So before we start, I wanted to just general shout out to Ashley McNamara, who is in the doctor hospital, and I'm wearing a super nice t-shirt she designed. So if she sees the video, hi Ashley. Cool, let's continue. I don't have enough time for anything else. So today I'm going to be talking about the robustness of Go. I proposed this talk thinking that Go was robust. And then I started thinking more about it. And I'm going to be talking about how actually maybe not that much. And then as soon as I started thinking, I was like, well, if Go is not robust, what is robust? And I tweeted about it, and people were like, C. And I was like, no, for real. People actually think that C is robust, which C is amazing, but it's also super fragile, and it's super easy to break things. So people then were like, oh, you should check out Erlang. So we're going to be talking about those two languages and runtimes and environments, talking about robustness. So we're going to be talking about first, what does it mean to be robust? What are the robust features of Go, or the features that make Go something, a programming language that I consider to be quite robust? What are the ones that actually kind of break that robustness, which is sad, but they exist? And then we'll give up on trying to make robust programs, because who cares anyway? And then, well, actually, Erlang is robust. So we'll talk about how is it that it is robust. GOTO is a great place to talk about it because, you know, Erlang was created by Joe Armstrong. That's walking around there. And then we'll talk about A New Hope, not the movie. So if you want the slides, they're online. You can follow up. You can use this beautiful QR code. I should have thought about actually using a link for those that read letters. But it's on speaker deck under my username, Campoy, so you can find it there. And real quick about me, I'm Francesc Campoy. I worked at Sourced, even though I used to work at Google for quite a while. I was a developer advocate at Google Cloud Platform, doing Go and machine learning. And also, as someone said, Just for Funk is a Go YouTube channel that I post every 2 weeks, except when my mic breaks, which is like the last time, so I didn't post a video. But it will come one day about Corba, because I hate my life. OK, so what does it mean to be robust? And this is kind of an interesting question, because like, when you think about robustness, there's many, many things that you can think about. Like one of them is like something very, very strong and very hard to break, right? But something very strong and very hard to break could also break for some other reasons, right? So when I'm thinking about robustness in the context of machine learning, of computer science, what I'm thinking about is not about really how it is when things go well, but how it works when things go wrong. It is the reliability, how easy it is to break something, intentionally or unintentionally, right? If I'm writing a program, how easy it is for me to write something that eventually will break by itself, or how easy it is for me to write a program that when things around it go wrong, the connection, a network connection fails, or a disk fails, or whatever, my program still runs or fails graciously, whatever that means in that situation. And what is the opposite of robustness? The opposite of robustness is fragility. And it's when things go wrong, they go even worse, right? The typical example, it's this. I don't know if you've ever seen these kind of errors. An error happened while displaying this error. Thanks. What are you going to do about this, right? Like, it is not about making something that works all of the time. It is about about creating something that works most of the time. And when things go wrong, it handles those as well as possible, which is better than this. So let's talk a little bit about Go itself. The first thing is if you go to why Go exists, you will see that it was created by a group of 3 engineers, Robert Grismer, Rob Pike, and Ken Thompson, while they were waiting for C++ to compile, which is kind of a joke, but kind of true at the same time. And one of the things that they were annoyed with C++ was not necessarily how long it is to compile, but actually the fact that there's many things that are very fragile, and one of them is the way you handle memory. It is very easy to write programs that are wrong, right? Actually, there's a very good talk about D, the programming language, which they talk about how hard it is to write an actually robust hello world in C++. It's amazing, because it's actually really hard, right? Go and Rust try to solve the same problem with different approaches. Go, what it says is like, ooh, I'm going to basically protect everything around yourself. Everything is going to be like very, very soft and no sharp edges, so that way you will not hurt yourself. Rust is actually, I'm going to make it a little bit more complicated, so the language, the type system of the language will avoid these issues, right? So there are different approaches to solve the same problem. Memory safety. Go has pointers, but there's no pointer arithmetics. What does this mean? Well, pointers are useful because if you have one object that is 1 megabyte in memory, you don't want to copy that object over all the time, right? So maybe what you want to do is actually say, you know, I'm going to pass the address to that. That is a pointer. Sure. What is that address plus 4? Who knows, right? So that is the thing that is not allowed in Go. Memory pointer arithmetics, it just simply doesn't exist. Unless you use the package unsafe, which is called unsafe for a very good reason. So you should not use it in general. There's also something really cool, which is Scape Analysis. And the Scape Analysis in Go is very interesting, especially for those that come from C and C++. It solves a very specific problem that most beginners in C and C++ will make that mistake. And people that are not beginners, they will eventually also do it. So I'm going to show that in a minute. Also, there's garbage collection, which means there's no dangling pointers. The dangling pointer being a pointer that you still hold that pointer, but what it's pointing to doesn't exist anymore, or is not something that you should be playing with. And automatic bond checks, which is very important too. All of this means that it is basically impossible to write a program in Go that will corrupt the memory, which is amazing. The only two ways to corrupt memory in Go is using unsafe, using CGO, which CGO is not Go, so it doesn't count. And the third one is to have a bug in the compiler, right? Which is on the runtime, which is kind of cool because it means that once that bug has been fixed, the problem has been removed from all of the problems written in Go, right? So you're basically solving classes of problems at a time rather than solving it per program. So what does that mean, that Scape Analysis? Well, it means that when you call new and you allocate something, it doesn't mean that this is allocated in the heap. It may be allocated in the stack, right? In here, for instance, what we're doing is, well, you're calling new, sure, but then you're, ooh, this is wrong. And I cannot edit. Why cannot I edit? OK, I cannot edit, so I'm going to ask you to imagine that that is actually returning star v. So it's returning the value of what it's pointed rather than the pointer, right? Which means that the pointer itself, the area in memory, does not escape. It's not accessible from outside the program. Therefore, that value can be stored on the stack, which means that the program will be faster. This is good for performance. On the other side, if you're allocating a variable int, 42, that looks like something you're allocating on the stack, right? Because you're not doing new. But then if you're returning the address to that, that will be wrong. If you do this same thing in C, that will be wrong. Because the pointer to v will be an address that you should not be accessing after the function value has finished. So that is a problem. And Go, what it will do is it will actually recognize that and just simply allocate it in the stack automatically. You do not care about this. You do not need to think about it, which is something very nice as someone coming from C++. And finally, the bound checks, which are important for correctness. If you're doing this, so you do a slice of 256 bytes integers, and then you access the position 512, who knows what that is? So this will actually panic. It will say, no, 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 this is not correct, right? This means that you're doing extra checks all of the time, which kind of brings performance a little bit down. But actually, correctness is way more important than performance. And in some cases, the compiler will be able to deduct that those checks are not necessary, and they will be removed. After memory safety, let's talk about type safety. So type safety, we have static typing. So as many other languages, basically, once you give a type to a variable, you cannot just change it. If a variable is of an integer, you cannot put a string in there. That just doesn't work. Similarly, we don't have implicit type conversion for numeric types. So if you have a float and an integer, and you try to add them, that will not compile. But also, if you have an int32 and an int64 and you try to add them, that will not compile. If you want to add them, you need to say explicitly, I'm going to convert this value to that other type in order to have two types that are compatible. This is important because that otherwise we would have type coercion. Type coercion is what JavaScript has, right? Where like the what videos, they're basically all about type coercion, where you have a string plus an integer, and it works. And a string minus an integer does something completely different, which is always confusing. So Go just doesn't allow that, right? More things are about interfaces. We do have interfaces, but they work, the satisfaction is done implicitly. Something like Python, basically, where in Python, that typing will say that if you have all of the methods that the algorithm requires, then you're good, right? But that is checked at runtime. In Go, that is checked at compilation time. We will say, for instance, fprintln expects the writer, so there's a method write. If you pass something that doesn't have that method, at compilation time, it will say you cannot use the type int as a writer in argument fprintln. Int does not implement writer because it's missing the write method, which is very nice. This is one of my favorite errors in Go. It's super easy to understand and clear. Similarly, you can do something like in C, the void star, or the crazy pointer. Has anyone used void star? OK. Void star, basically what you're saying is YOLO of types. It's who knows what's there. Once you say it's void star, you forgot everything about it, right? In Go, we have the empty interface, which is kind of similar because you can put anything in an empty interface. But we're keeping the type. We're keeping the type information. So afterwards, if you try to say v, which was 42, that integer, I'm going to use it now as an empty interface. So I forgot what it was. And then I'm going to say, and now I'm going to use it as a string. That will not work. And that will not work, and it will be a check at runtime, not compilation time, because that'd be basically impossible to do. But at runtime, we'll say, no, you can't just not do this. If you've done C++ and you've done things like, I even forgot the name, reinterpret cast, those kind of things where basically you're saying, just let me know, I know what I'm doing, let me do it, I know what I'm doing. You can do also that in Go, unsafe package again. One more thing that, even if it looks weird, it actually helps with detecting errors early, is the fact that in Go, if you never read a variable, a local variable, it will not compile. And it's interesting because this is an error. In this error, it's something that lots of beginners in Go write very often. What you're getting when you're looping over S, which is a slice, and which is actually an image, it's a matrix. So you're looping over that, and you're getting a copy of the rows. And then you're getting a copy of the cell. And then you're assigning something to that cell. Turns out that that is a copy, that is not a reference. So when you try to write something there, you're actually not modifying anything. So you're declaring a variable, never reading from it. That's suspicious. That doesn't compile. This error is the kind of thing that if it wasn't like this, it'd be super hard to see. Because when I'm reading this code, this looks super nice. I don't see any problem with this. The compiler will tell you. Then, the famous thing, in Go, there's no exceptions. Instead, we use errors. And if you've written any Go, you know if error is not nil, then something, right? So we do those checks all of the time. They're part of how we write code. And this is something that I could give a whole talk about it, right? But there's actually a really whole talk about it, which is very good, by Dave Cheney, called Handle Errors Gracefully, which is a really good talk explaining how we do errors in Go. The important thing for robustness is what happens when you have exceptions. And exceptions are banned at Google for C++. Therefore, it kind of makes sense that when they create a new language, they also ban exceptions, but directly by not adding them to the program, to the programming language. If you see this code where you're saying, oh, I'm going to provide this function where whatever you're going to do, I'm going to do it inside of a mutex, right? Mutual exclusion, only one function at a time could be called, no matter from how many places you're running this. What happens if f throws an exception? Well, the mutex will never be unlocked, the program will block forever, and the system is down, right? That is a serious problem. So that's why in Go there's no exceptions. And if you know Go, you'll be like, but we'll get there later. So what about channels? Why are these part of robustness? Writing correct concurrent programs is really hard, really, really hard. And I'd say that actually the way Go works and the concurrency features that it provides allows Gophers to write better code that is easily correct. So in very quick, the way it works is we have Go routines, which are the cute Gophers. The cute Gophers communicate with each other using channels, which are basically like Linux pipes, but they're typed and concurrently safe to use. And then there's one more thing, which is select, for when you want to do multiple things over channels. Those are the three concepts you need to know about concurrency. And with this, you have everything, right? So this is actually really cool. OK, so we've talked about all of the things that are good. Let's talk about the things that are not that good. Just want to make sure I'm on time. OK, yeah, cool. Cool, so let's talk about the things that make Go fragile. Mutable state that is shared, that is very, very wrong. If you ask any functional programmer, they will tell you that mutable shared state is the worst single thing you could have in a programming language. So what happens here, what we have is we have a function ticker that every second is printing the value of a counter. And then we have an endpoint for a web server that every single time it's hit, it just adds something to the counter. So when you run this, it works. But this is wrong, right? Why is this wrong? Does anyone know? You know. Yeah, so there's two things. There's every single request will be handled by a different Go routine. So you could have two different Go requests, adding one at the same time, and only one of those will actually work. Even worse, the behavior might be undefined, because all of a sudden you get a data race. At the same time, you could be writing at the same time that the ticker is reading, which is also a different kind of data race. But when you run it, you don't see this. When do you see this? Well, actually, when you have enough high load, and all of a sudden you start missing counters. And good luck figuring that out, right? Luckily, we have dash race, which is the data race detector, which is super nice. And when you run the same program with the race detector enabled, which you only need to add dash race, super simple, you will get warning data race, and it will tell you exactly where it was reading, where it was writing, or if two Go routines were running at the same time, where were those lines, what were the ID of the Go routines, all of these things, in order to be able to figure out what's going on quite easily. Now, the problem is that the data race is not free. It makes your program go slower. So in my personal opinion, you should run your test with data race enabled every single time. I don't care. If it's slow, make faster tests. I don't care. It should be data race enabled, because it's really important. And maybe in production, when you're deploying a canary, you could actually also deploy it with data race enable. See if it's working. And once it's working, then redeploy with a data race enable and send production traffic, right? That way, every single warning data race, that's a new issue. That's something you need to fix before you deploy to production. NeoPointers. I gave a whole talk about NeoPointers. NeoPointers are the $1 million mistake, or $1 billion mistakes. I don't even remember, but it's a very expensive mistake, right? I forgot the name of the person that invented pointers now. But he said, actually, Hoare. Yeah, C.R. Hoare. He invented pointers, and he said it was the worst mistake he's ever done. And then the Go creators come, and they're like, you know what? Let's not have nil pointers, but also nil slices, nil channels, nil maps, and nil function. And all of these are going to be nil, so yay, everything's going to fail. I gave a whole talk at GopherCon in 2016 about this, and I invite you to watch it. The whole idea of this talk is, yes, nil pointers have bad sides, but actually they're very useful in Go. If you have a pointer to a type, calling a function in it doesn't necessarily fail, which means that nil values are actually useful in Go, especially for slices and not functions, but slices and channels and receivers and all of this. Nil values are totally fine. For some others, like nil maps, they're actually the way they are. They're not great, but they're there. And lack of generics. Yes, Go does not have generics, which is good in some sides, in some ways, because it makes the programming language easier to understand and simpler to learn and all of these things, which is great. But when you don't have generics, there are many things that are hard to implement. One of them is monads. One very nice way to handle errors is by using monads. The error monad or the maybe monad are great for this. And I gave a talk at GOTOchgo in 2015. That was a long time ago. So in 2015, I gave a talk about what if we try to do monads in Go. So I tried, and it works, but it's so painful that it's not worth it. It is a really bad idea. But the whole point is that the API you end up having is actually quite nice. So I'd say that if Go had generics, the error handling we do would be nicer and easier to manage. There'd be all downsides. The programming language would be harder to understand. But I don't know what we should do. I'm not saying we should have generics. I'm just saying there's good things about them. I also said Go doesn't have exceptions. Instead, it has panics. Sure, what is the difference? Not much. They're actually basically the same thing. Panics are the same thing as exceptions. They're just not called exceptions because panic, it's more about, this is when you're really panicking. Literally, there's nothing else you could do, right? So for instance, I don't know, you try to allocate memory. Turns out there's no more memory. What are you going to do? You could return nil, and that will fail later, or you could just fail now. There's no point in trying to continue, right? So that's the point where you panic. I like to say that panics are used exceptionally, unlike exceptions. Exceptions are a thing that you see all the time, right? Panics are really, really exceptional. And the way you recover from them is by using recover function. The recover function, what it will do is, will be called always inside of the defer function, which means that that will be called at the end of main, the function where you're defining it, no matter what, right? So even if there's a panic, deferred functions will be called. In there, you can go recover, and that will check if we got there because of a panic. And then it will give you that value. So that's how you can handle these errors, which is pretty nice, because then it means that, yeah, we have panics, but we can recover from them. So we can still keep our program running, which is what we want. So another HTTP server. This HTTP server is simply whenever you call, when it receives an HTTP request, it panics, saying, boo. What happens? Well, the HTTP package actually recovers from that mistake, and it will print a message saying, hey, there was a panic, but don't worry, we'll keep going, we're fine. And it just continues going. The HTTP server will not go down. Nice. Now you do this. Go, panic, boo. Now panic happens in a different Go routine. So the call stack that we're going up does not include the HTTP package, which means that it does not include any recover, which means that the panic will not be caught, which means that everything will crash. The whole HTTP server will crash, right? So no matter how safely you write your code, anyone can write go panic and take your server down. So Go is not robust, which is sad. But at the same time, if you think about it, no matter how robust your programming language is, if your computer catches fire, who cares? And by catching fire, I don't necessarily say catch fire, but unplugging the computer, the network goes down, whatever could happen to the computer. Or even for some reason, the CPU stops working. Like, these things happen, right? They don't happen really often until you have billions of computers, and then it happens every second. So these are things that you cannot really deal with. So there's no point in trying to do robustness, so we should just give up and go. So thank you. No, just kidding. No, but this is an important point, right? Because no matter how good your programming language is, it will not be robust. There's no way you can do that. But Erlang is robust. Joe Armstrong gave a talk about how you can make incredibly robust programs that run forever, self-heal, they're amazing, miracles of computer science. And not only that, but they achieve 9 nines of availability, which is, by the way, totally false. You can search it and find that this is not correct. But still, even if it's not 9 nines and it's only 5 nines, that's still amazing, right? So Erlang gets it right. So how do they do it? Well, I spent a lot of time doing this Photoshop of Joe Armstrong because I really like his position on this image. I did actually GIMP, or GIMP? I actually don't know how to pronounce it. Anyway, there's a really good talk that he gave. It's called Systems That Run Forever, Self-Heal, and Scale. And I definitely recommend everyone to go watch it because it's one of my favorite talks. It's an InfoQ. And in those, he talks about 6 rules that are necessary for programming language or system in general to be robust. The first one is isolation, right? Which means that if something fails, it's fine that component will fail, but the rest should still be okay, right? So in Go, if you have a Go routine that panics, and that panic is not caught, the whole system goes down. So Go does not provide isolation. So, boo. Concurrency. Erlang provides concurrency. They have processes which are actually very, very similar to threads, to Go routines. Super cheap, and you can run thousands, millions of them in a single machine, which is very nice. The system of concurrency is a little bit different. In Go, we have channels. Erlang has actors. There's a really good interview, which I forgot to add, but there's a very good interview with Joe Armstrong and the creator of the actor model, talking about how the actor model is better than communicating sequential processes, which is the one with channels, because you can implement channels with actors and not the other way around. So it's pretty powerful, but they're really similar. So I'd say Go concurrency, pretty good. Failure detection. So when something goes wrong, we notice it, right? In Erlang, you have things like monitors. So basically, when a process fails, you can get a notification from somewhere else saying, hey, that failed, right? And then you can ignore it, or you can do something about it. In Go, well, we detect it because the whole program fails, right? So it's easy to detect. But there's not much more than that. They don't have fault identification. And fault identification is also quite interesting because it is not about knowing that something failed. It's about knowing why it failed. And this is quite interesting because in Go, you could parse the panic, like maybe. I do not recommend trying to do that at all. Like, please don't. In Erlang, when a process fails, you can actually say, hey, I'm failing. This is the reason why, which could be something from a stack trace to a string or any other value. Joe Armstrong in his talk talks about you could send a whole database, which I do not recommend either, but you do you. And then you can act on it, right? Go doesn't really do that. Live code upgrade. This is something that I have never used with Erlang, but it's basically the idea of being able to deploy a new chunk of a program while it's running and not take it down and just refresh the code and just keep running. Which really reminds me of this picture because it sounds really dangerous, but it actually works really well. Go does not do this at all. Like, don't even think about having this ever. I do not think that anyone wants this in Go. So you cannot do this. What's the point of this? Well, if you need to stop the program to upgrade it, it means that in between that part where you stop it and you start it again, you might miss request. So you have a little downtime in there, right? So that's why the live code upgrade is important. And finally, he also talked stable storage. And I would like to talk to him about this because I'm actually not that sure about what he means. Stable storage is a storage that allows you to basically do transactions. So when you do something on it, either it works completely or it fails completely. But there's no like mid states, right? So for instance, if you have a SQL database, when you do a transaction, you have that. If you have other databases, you might have the same. But for instance, if you're writing to a hard disk, unless it's a transactional file system, very often if the program fails, you might end up with corrupted files, right? That is not stable. So stable storage is important to have a distributed system that is robust. And all of these 6 rules, allows you to then say, let it crash, which is something that Erlang proposes, saying, if something's wrong, just crash. Thank you. If something's wrong, just crash. Don't worry about it. Someone else will fix the mess, right? This is only you can do it once you've actually figured out the 6 rules before. Go doesn't do it. Therefore, let it crash for Go is a bad strategy. So, who wins? Erlang versus Go? OK. Erlang versus Go? Good. I said at the end, failure detection, yes, because kind of. Live code upgrade, definitely not. And stable storage, I mean, Erlang has stable storage because they use Negia, which is a database. In Go, you can also use that database. So sure, right, why not? Like, that's fine. In my book, that means that we have stable storage for Go too. And this is my best slide. Look at this. Work. Come on. No, there was a beautiful animation in there. Wait a second. There you go. Thank you. I spent a lot of time doing this. So what is the new hope? The new hope is Kubernetes. Why? Well, because with Kubernetes, you actually are able to satisfy the rest of the rules that Go doesn't bring by itself. Kubernetes. So isolation. Does Kubernetes provide isolation? Yes, lots of it, like everywhere. First of all, it runs on containers. So if a container goes down, it doesn't bother anyone else. There's namespaces, so you can even isolate those containers from interacting with each other. You have multiple nodes, so if a machine goes down, nobody cares, because there's other machines. And not only that, but you have multiple clusters. So if a whole country loses electricity, well, there's another country where you have another data center, you're fine, right? So isolation, perfect, amazing. Concurrency, well, we already had it with Go. Basically, the only thing we're getting is you have more parallelism. You'll be able to run more replicas around different machines and stuff like that. But it doesn't really add more from that point of view. Failure detection. This is actually where Kubernetes is amazing, because it will monitor your containers for free, right? So it will actually be checking all the time, are you OK? Are you OK? Are you OK? You're not OK? Buy new one, right? That is what you want. If something fails, it will just be restarted automatically, which is what Erlang also does. Also, restart policies allow you to even detect those things and do things accordingly. When something fails, it doesn't need that it should be restarted automatically. Maybe you want to do something else. You can also do those things. Fault identification. You log stuff, so you can go read the logs. No, don't do that. I mean, log stuff, for sure. But do not read the logs to detect what happened, like with a machine. That's a really bad idea, I consider. But there's dev termination log, which I had no idea it existed. But when a container goes down, you can write to that file, and that will be part of your container specification, of your pod, actually. So if a pod goes down, you can write there and then ask, hey, that pod fell. What happened? And you will get the message. So you get exactly the same idea as in Erlang. You have that concept of being able to leave a message. I'm about to die, but this is why, right? Live code upgrade, sure. We have liveness probes and readiness probes, and the live rolling updates. What is this? We have rolling updates, which means that you can, yes, I got it. You can migrate from V1 to V2, or V1 1.2, V1.2, by saying, hey, I had 3 pods in version 1, and I want to end up having 3 pods on version 2. Please figure it out. What Kubernetes is going to do is start a new pod for version 2. And once it's not only live, but ready, imagine that you have a system that takes 1 minute to start. It's running, but still not ready to answer requests. That is the difference between liveness and readiness. So once it's ready, it will take down one of the version 1, then start a new one, wait for readiness, stop one, and continue like this. This means that if for any reason something is wrong, the deployment will stop. So you will not have any problem of downtime. because a new version is broken. Unless your readiness probe is also broken, and then you're out of luck. And finally, stable storage. Sure, we already had it before, so why not? But also Kubernetes comes with etcd, which is a very good example of stable storage. You can also use SQL databases or any other database that you want. So in conclusion, so Erlang and Go, if you compare them, Erlang clearly wins. But Erlang is not robust. Beam is. And if you compare to that, and you compare Erlang on top of Beam versus Go on top of Kubernetes, you will see that one, I don't know how to do animations, but second, that this is actually exactly as robust as Beam. So Kubernetes is not something revolutionary for those that were already using Beam. If you're using Erlang or using Elixir, that's amazing. You're already using a system that has been incredibly robust for many, many years. But for those running different programming languages, such as Go, but you could also be writing any other language, literally. You could be writing in Java, you could be writing in JavaScript. Kubernetes will provide that extra layer that allows your programs to be more robust. I wanted to end up thanking two women that helped me write this talk, Veronica and Miriam. Veronica is really good at Elixir. Miriam is really good at Erlang, and they made my talk much better, so thank you to them. And I'm done, so thank you very much, and we have some time for questions.
All right, yeah, thanks, Francesc. And yeah, if anyone has the app, feel free to submit questions through the GOTO Chicago app, or raise your hand if you have something to ask. I have one to kick it off, just because I don't know the Go ecosystem well. Off the top of your head, what do you think's the most robust, commonly used Go program, or even just that you've seen? Like, how can you get to 5 nines with a really good Go program? Can you get to
Kubernetes is running Go.
Yeah, there you go.
So I'd say that probably Kubernetes, the fact that it's running Go, says that Go is quite robust.
It's impressive.
But it's not about the fact that it's running Go. It could be running in any other language and still be as robust, because it's the architecture that counts, right? Kubernetes is a rewrite, an open source version of an internal system in, at Google called Borg that is written in C++, right? So it's not about robustness of the language itself. It's about the architecture that you write around.
Cool. We got a question on the app asking about sort of dependency management and versioning in Go, sort of in comparison to like Node.js or Maven or something like that. And asks why didn't Go sort of embrace the sort of modern, or not even
Modern,
whatever.
wow.
I think things are going in a different direction now. Why didn't Go make the choice that a lot of other languages that came out in the early 2000s to have version dependencies and distributed source control and everything?
So I guess that the most important thing to know is that we have not really decided yet. We've been playing with, so Go took a very long time to have a version management system because it comes from Google, where we have one repo. So we don't have versions. That's pretty easy, right? Now, not everybody should do that. Like, it's a not very good idea if you have multiple teams and don't have many engineers to maintain your repo. So we started doing it by vendoring, because it's the simplest way, where you have all the power to do whatever you want. Basically, you copy that piece of code that you depend on, you put it inside your repository, and then you want to upgrade, well, you go, you get the new version, and you put it there. The problem is that upgrading that can be painful. So that's why we created tools around it. DEP is the tool that I still use, personally, that allows you to manage this in a very simple way. Basically, you're able to say, hey, find all the dependencies that I have. Once you bring your program, it will store them, and then when you want to upgrade to something new, you just edit one file saying, actually, I want to go to the next version, and it will do it by yourself. There's a new thing called Vigo, which is what everybody is supposed to be trying out now. I have not tried it yet. And it's a similar idea, but the most important difference is that Node.js and NPM and all of these package managers, very often what they do is they allow you to have lots of power on what version you want to run, but the default is the latest version, which is dangerous. So in Vigo, what we do is the other way around. So if you say 2.1.0, well, 2.1 dot nothing, we're going to try to use 0 as long as it's available. And if you want to upgrade to something higher, then say it. Because otherwise, what happens if a new version comes, you're just deploying, and without even noticing, you're deploying new code. Right? So Vigo and Deb, the main difference is that Vigo is much more conservative. Yeah.
Cool. For people who don't know the ecosystem well, would you say there's a talk or a blog post somewhere on like, hey, these are the best practices, this is how you should actually use like GoDep or Vigo? Are there any you can point us to?
For Deb, I'd say, I mean, the documentation of Deb is amazing, but also there was a really good talk by the creator of Deb, which I forgot his name. He's going to kill me. Sam Boyer. He gave a keynote at GopherCon last year about that, explaining how it happened and the decision taken during the process and stuff like that. Very good talk. For Vigo, there's 2 blog posts written by Russ Cox from the Go team that explain this very well.
Okay.
Yeah.
Cool. Any other questions from the audience? Okay. I've got one. So let's imagine that GoTo comes out and it has Erlang style like hot code swapping, and you could magically swap out like function implementations on a live Go routine or something.
Yeah.
Would you use that, or would that be a terrible idea?
Yes and yes. Yes, it is a terrible idea, I'd say. But yes, I would definitely use it because I love, so I'm sure you also Sonic Pi. Sonic Pi, based on the idea that you can actually refresh a function and keep running. Yeah. In Go, that's impossible. Simply impossible right now. I'd love to be able to do that. Because it's statically compiled, yes, and we have plugins, but those plugins are loaded dynamically, but only once. So then I wrote a thing that is disgusting. So please, I'm not even going to say where it is. But basically what it says is whenever you try to load a new file, it will say, I'm going to compile it and load it, and I'm going to give you a random name, so that way you have a new thing. Yeah. The problem is that, of course, there's no garbage collection for that. So after a couple of minutes, your program crashes. But that's OK.
Yeah, a lot of people really praise Go's like small static binary outputs for things like building like Scratch Docker files and really cool stuff like that.
Yeah.
Do you feel like that's the future? Do you feel like a slightly more dynamic like hot loading thing has benefits, like real benefits for like sort of future systems?
I've seen a system that got me really excited, which is so Go and its runtime have a pretty clear API, right? And what someone was proposing was saying, well, why don't we use this API? And the runtime, rather than say it's a Windows runtime or a Linux runtime or whatever, it's a distributed runtime, right? So that same program, whenever you're running a new Go routine, that new Go routine might be running in a different machine, which would make Go be more like Erlang over Beam. That is super interesting, but it's a research problem right now. So if that happened, I think it'd be really interesting because then it would allow Go to be as robust as Go plus Kubernetes without needing Kubernetes. And I think that the runtime below Go could actually be Kubernetes, which is kind of meta, but it could work. And I think that's super interesting. That's something that I would like to see one day.
So like Kubernetes would basically become a Go routine scheduler in a way?
Yeah, yeah. And it knows everything, so if you have channels between 2 Go routines, because they're going to communicate, so you should be running the same machine if possible, and things like this.
Wait, what's the name of that project?
It's actually something that I heard internally at Google, but it was open source. I know I can talk about it, because I don't work at Google anymore. So no, but also because it was a public blog post, but I don't remember the name.
Cool. I'll have to look that up. Cool. Well, thank you so much, Francesc.
Thank you.
Last round of applause.